Stress. We all have it. And I think it's safe to say most of us try to avoid it. Just imagine a few scenarios here. You're at the beach. Nobody else in sight. The place is yours. How relaxing is that? I doubt you'd want to be anywhere else, right? Suddenly, hundreds of beachgoers descend on your oasis, taking up valuable real estate, making noise, and generally stressing you out. What do? You probably pack up and leave the beach, right? Maybe you're standing in a checkout line at the store. If one line suddenly grows longer than the others, what tends to happen? Of course, business patrons leave the long line, distributing themselves among the remaining shorter lines. Maybe people outside the store see the lines as they approach and start to rethink wanting to be in there at all. Maybe you like to take a particular road to work, but suddenly everyone in town gets wise to your secret route, flooding it with cars and traffic. Now you're probably thinking about taking a new route to work. Now, all of these examples have two things in common. A change to the system caused a stress, and you reacted in a way that relieved the stress, at least somewhat. The more people on the beach, the more likely some folks will leave to get out of the crowd. The more people in the checkout line, the more likely some are to abandon that line to find a new one. The more cars on a given road, the more likely people are to divert and look for a less crowded street. So, what does this have to do with chemical reactions, you might ask? Well, yet again, human behavior gives us a metaphor for the behavior of molecules and atoms. When you take a system humming along at a nice, comfortable equilibrium, then apply a stress, the system is going to shift itself in a way which partially relieves that stress. As simple and intuitive as this may seem using our analogy, it took scientists quite a while to discover just how common this phenomenon is in chemistry and how powerful of a synthetic tool it can be. Last time we took a look at equilibria and equilibrium constants, as though they were the ones in charge of the situation. We were simply at their mercy when it came to running reversible chemical reactions like the synthesis of hydrogen iodide from hydrogen and iodine gases. But we never really considered that the temperature and pressure conditions under which our reactions were taking place can be changed. When they're changed, the equilibrium constant for a reaction can also change, causing a shift in that equilibrium that allows us to, at least partially, bend an equilibrium to our will. Last time, Claude Louis Berthollet was the inspiration for our lecture. He was the first to give serious thought to the notion that reactions might run in reverse, creating dynamic equilibria for certain reactions. This changed our way of thinking about how matter interconverts, forcing us to consider the possibility of equilibria in chemical reactions. But the real inspiration for how to manipulate equilibrium processes would have to wait 2 more generations for a man by the name of Le Chatelier. Le Chatelier will ultimately help us to unify Gibbs' ideas about free energy with Berthollet's brainchild of chemical equilibrium, a fitting accomplishment since Le Chatelier shares a country of origin with Berthollet, and he translated much of the work of Willard Gibbs, of Gibbs' free energy fame, into French. So Le Chatelier, being classically trained in France, was no stranger to the concept of chemical equilibrium as it had been advanced by Berthollet. Now, this was nearly a century earlier. In fact, Le Chatelier's own father was influential in the development of French aluminum, iron, and steel industries. So it probably came as little surprise when a young Henri Louis expressed an interest in chemistry. It might also explain his acute interest in the effects of temperature on reactions. Now, this might invoke images of our friend Svante Arrhenius, who's commonly credited with linking temperature and reaction rates for irreversible processes. But what distinguishes Le Chatelier's work from Arrhenius is that Le Chatelier was interested in the effect of temperature on equilibria. His study of equilibria under varying conditions led him to a conclusion that is known as Le Chatelier's principle. Le Chatelier's principle can be summarized: a chemical system placed under a stress will shift in a manner that relieves that stress. That's it. Chemicals don't like to be stressed any more than you do. If we alter the conditions surrounding a particular chemical system, be they concentrations, temperatures, or pressures, the system will try to undo our changes by undergoing a shift in its equilibrium. So how can such a simple observation open the door to bending equilibria to our will? Let's take a look. Now, we saw last time how concentrations of both reactants and products can dictate the direction that a system will shift to reach equilibrium. We illustrated this using the reaction quotient. Starting with very high reactant concentrations tended to make smaller reaction quotients, ensuring the system would shift toward products. And of course, starting with relatively high product concentrations would cause the reactant to run in reverse to establish its equilibrium. Now, imagine a system already at equilibrium. What happens if we disturb this equilibrium by the addition or removal of products or reactants? Well, let's take a look at how this should affect a simple reaction to help us understand better. Take a look at our familiar reaction here, NO2 in equilibrium with N2O4. Now, let's assume that we're going to change concentrations here. Let's pretend this is the equilibrium mixture. Now, we know the equilibrium constant is not equal to 1, but that's sort of what I've made it look like here, or at least very close to it. But I've done this just so that we can demonstrate the principle. Now, I've defined N2O4 as the product and NO2 as the starting material in my equilibrium. And they're confined within a certain space. Now what I'm going to do is consider that equilibrium. Right? There's an equilibrium constant that governs it. I'm not sure what it is at this point because I don't know the temperature. But let's just say that it is what it is. This is our equilibrium constant. And we have Q, our reaction quotient, that we're going to think about. If our system is at equilibrium right now, there shouldn't be any shift whatsoever. But I'm going to put the system under stress now that it's already at equilibrium. I'm going to make a change. I'm going to add extra NO2, increasing its concentration, therefore changing the value of Q. Now the system is going to immediately abide by Le Chatelier's principle and try to find a way to relieve the stress that I just created. Well, the stress was I increased the concentration of NO2. And in order to fix that problem, what can the reaction do? How can this reaction decrease the concentration of NO2? Well, of course, the reaction can shift. The equilibrium can move in favor of N2O4, bringing Q back in line with the ratio that we expect from the equilibrium constant. So this is an explanation of exactly how and why concentration can be used to manipulate equilibria and maximize the amount of whatever reactant or product we want to be present in the system. Let's start our next inquiry right where Le Chatelier did. The son of a materials engineer with great accomplishments in the processing of metals, it wasn't a great leap for Henri Louis to take an interest in high-temperature chemistry. The key to understanding how Le Chatelier's principle applies to temperature is to think of heat as a product or reactant in a chemical process, just like any other reactant or product made out of matter. Now ask yourself again, what is temperature? It is molecular motion, it's heat. And where else have we encountered the idea of heat? Thermochemistry. Remember that reactions can either generate or consume heat as they progress. Those reactions which consume heat from their surroundings are called endothermic, while those that release heat into their surroundings are called exothermic. In our lecture on thermochemistry, we indicated the flow of heat during a reaction using a symbol delta H. When delta H is positive, the reaction is endothermic, consuming heat as it progresses. When delta H is negative, the reaction is exothermic, releasing heat. So let's go back to our reaction of NO2 and N2O4 and think about how it deals with heat or how it interplays with heat. This reaction, as I've written it, is an exothermic process. The conversion of 2 moles of NO2 into a mole of N2O4 releases 57.2 kilojoules per mole of heat. That means that I can think of heat as though it were a product of that reaction. So instead of showing my enthalpy this way, let me just instead think of it as generically being a reaction where heat is a product. Now, that gets us more in line with thinking about Le Chatelier's principle, doesn't it? What happens when you increase or decrease the concentration of a product? You shift an equilibrium, don't you? But this time, it's not a physical product. Instead, it's heat that we're thinking about. So if I have a system like this one, it's all NO2. The system can fight any temperature changes that I try to make by pushing the equilibrium one way or the other. Specifically, when NO2 comes together to make N2O4, it releases a certain amount of heat into the system. So think about this. If the system is nice and happy here, and I cool it down, right, put it in an ice bath, put it in the refrigerator, you name it, any way to get the temperature down, Le Chatelier's principle says that reaction is not happy anymore. I took some heat away, and it is going to try to undo my work. It's going to try to produce heat. And how is that accomplished? By shifting the equilibrium in the direction of N2O4. Make a new molecule of N2O4 in our system, and it heats up again. And if I continue to try to cool the system down, the system will continue to battle me, making more and more and more N2O4. So I can control this reaction simply by modulating the temperature. If instead it were my goal to make more of the NO2, I would simply make sure that I raise the temperature of the reaction. Le Chatelier's principle again predicts it's going to fight me and go right in the other direction. So altering temperature in this case is not that much different than altering the concentration of a product or a reactant. It still abides by Le Chatelier's principle. We're back in Osmond Lab at Penn State University again. This time to see if we can observe Le Chatelier's principle working on the NO2-N2O4 equilibrium, just as we had predicted a few moments ago. Now to do this, I'm going to use some sealed glass tubes that are filled with NO2, nitrogen dioxide gas, and to change the temperature pretty dramatically, I'm going to use a dewar filled with liquid nitrogen, which has a temperature of minus 197 degrees centigrade. Then we're going to compare the two and see if we can observe the effect on the equilibrium between the dark orange-colored NO2 gas and the relatively colorless N2O4 gas. All right, let's get started. Here are my two tubes, as you can see, both currently at room temperature, both containing roughly the same amount of NO2 gas and therefore the same color. But we're going to give this one a bath in liquid nitrogen, lowering the temperature of the system. And you can see here clearly the liquid nitrogen itself is boiling under the influence of the tube being placed into it, but soon that will settle down, and the temperature of the gas inside the tube will reach the same temperature as the liquid nitrogen that it's being dipped into. So now we can compare these two and see what's happened as a result of lowering the temperature so dramatically. It's a fairly obvious effect, isn't it? We've converted most, if not all, of the NO2 into the N2O4 gas. Now, as I slowly warm the tube back up, we'll be able to see this equilibrium slowly shifting back in favor of the NO2. So I'm just using a little bit of heat from my hand, being careful not to freeze it to the tube, to heat that tube back up. And as you can see here, as it gets a little more comfortable for me to do that, we're already beginning to see the transition back as the equilibrium shifts. And once this tube reaches room temperature, of course our equilibrium will be right back where it was. So, because this is an exothermic reaction, the conversion of NO2 to N2O4, lowering the temperature removed the heat and caused the equilibrium to shift. And then, of course, adding heat back using my hand, I'm able to shift my reaction back in the other direction until we're getting pretty close now to where we're back. So as you can see, we got a little bit more warming up to do, but clearly we've shifted the equilibrium yet again. The difference between the equilibrium between NO2 and N2O4 in our liquid nitrogen and our room temperature example was stark. It's so stark that sometimes it leads us to forget that equilibria shift in a sort of a gradient-style fashion. They're not just on or off. They're slowly and constantly shifting as we change conditions. And to demonstrate that, I'm going to use the same two tubes filled with NO2 gas that we did previously here in room temperature water. But I'm going to place one into a bath of warm water, which I have over here, and one into a bath of ice water, changing their temperatures rather slightly in comparison to what we just witnessed. And we'll see what that does to this equilibrium. So again, one tube will go to my warm water bath, and the other tube to my cold water bath. And now we're going to wait a few moments for these to equilibrate from a temperature perspective, and we'll come back and see how they look.
So a couple of minutes have now passed, and we're ready to take a look at the effect of slight temperature changes on this equilibrium. So here again is my warm water bath, and here's my ice water bath. And if I remove the two tubes, hold them against my lab coat here, you can see very clearly that the equilibrium has shifted somewhat, but not quite as drastically as before, proving again that the shifting of equilibria in response to Le Chatelier's principle is a sort of a subtle gradient type of process. It doesn't happen all or nothing. Instead, equilibrium can be modified very carefully by very carefully adjusting the conditions. I'll put these back in my room temperature water and let them get back to their room temperature equilibrium.
So we just saw that temperature can clearly push reactions backward and forward, particularly when there's a large change in enthalpy between reactants and products. But temperature isn't the only condition that can matter. Let's think of another way that we can stress gas phase reactions like our NO2-N2O4 equilibrium. What about pressure? Just as before with temperature, let's pause for a moment and think about what pressure really is. In our lecture on kinetic molecular theory, we thought about how pressure is generated by the collision of gas particles with the walls of their container. More frequent collisions means more pressure. So if I increase the pressure on a system of gases like NO2 and N2O4, and Le Chatelier's principle applies, how might this system shift in order to undo my pressure change? Well, let's take a look. Here's our reaction star for the day, NO2 in equilibrium with N2O4. Now let's think about pressure. Well, pressure is related to several things, not the least of which is the number of moles of gas that are present. Remember the ideal gas law. So in this case, I have a reaction in which I have 2 moles of gas as starting material in equilibrium with 1 mole of gas as my product. So this system can change the number of moles of gas present by shifting. Let's keep that in mind. With that in mind, let's think about a simple system. Again, I've only shown the NO2 molecules here, but there certainly would be some N2O4 present in equilibrium with it here if this were a valid equilibrium. But for now, let's keep our eyes on those NO2 molecules. I'm going to squeeze this system down. I'm going to increase the pressure that it's under simply by changing the volume. So I'm going to force this volume down, and when I do so, the pressure of the system is naturally going to go up. Right? We understand this from our gas laws. But again, Le Chatelier's principle says this system is going to sense that increase in pressure and immediately try to take steps to undo what I have just done. I'm pushing down on it, decreasing the volume. I'm in control of the volume. I've got it at a constant temperature, but I'm increasing the pressure. What can this reaction do, right, to change that, to undo my work? Well, of course, it can change the number of moles, because remember, the ideal gas law contains a term for number of moles. I'm controlling the volume, I'm controlling the temperature, but the reaction's got control over how many moles of each thing are present. And all it has to do to reduce that pressure is reduce the number of moles present by reacting in order to form the N2O4. Fewer moles of gas means a lower pressure. It's partially undone the work that I just did. Le Chatelier's principle. Just as we were able to do with temperature, we can observe the effects of pressure and Le Chatelier's principle on an equilibrium using the NO2-N2O4 equilibrium. Now, to do this, I've got a syringe that's filled with NO2 gas. You can see the orange color here against my white lab coat. Now, what I'm going to do in a moment is compress this plunger to decrease the amount of volume. In other words, I'm going to increase the pressure. And in doing so, I'll be pushing those NO2 molecules closer and closer together, making the gas inside turn darker in color. But very shortly after that, you'll see a change. You will see that the gas inside begins to lighten again. And this is the chemical equilibrium shifting towards N2O4 in response to the pressure that I've applied. So I'm going to do this really quickly here, but we'll slow it down for you so you can see exactly what happens. Here we go. So what we just saw was the gas inside the syringe darkening quickly in response to me applying pressure, but then fairly quickly as well, turning light again as the equilibrium shifted towards N2O4 based on Le Chatelier's principle, trying to undo the increase in pressure that I had just applied. Le Chatelier's principle is remarkably useful in the field of chemical engineering because it gives us a way of thinking about how to push equilibria in ways that produce maximum yields of various products. In fact, Le Chatelier's principle is beautifully illustrated by one of the most influential chemical inventions of all time, one that has truly altered the course of human history over the past 100 years. Consider this. Many experts estimate that at best, the Earth can only support the agricultural activity needed to feed about 3 to 4 billion people. If we were to use every farmable acre of land, relying on crop rotation and our best farming techniques from about 2 centuries ago, the population of Earth today would be much smaller. Global famine would almost certainly have culled the population by now and reached a steady state of human population. A grim outlook. And yet, here we are, all 7 billion of us, most of whom are well fed. So, how did we accomplish this? Well, we accomplished it by bringing chemistry to bear on the issue of agriculture. You see, about 200 years ago, a German chemist by the name of Justus von Liebig had the realization that chemistry and agriculture were inextricably linked. He noted that by adding certain chemicals containing nitrogen to soil, he could encourage greater numbers of more productive crops to grow from them. Of course, I'm talking here about fertilization. And one of the most effective fertilization techniques involves adding usable nitrogen to soils via compounds like ammonium nitrate. Liebig's seminal work on fertilization is all well and good. It gives us the potential to improve crop growing potential of the earth. But you then have to ask yourself, where will that nitrogen for the fertilizer come from? For 100 years after Liebig's work, it came from mineral deposits of saltpeter dug from the earth, and of course the droppings of certain animals that were collected and used in this fashion. But supplies of these materials are limited and sometimes hard to acquire. Nonetheless, these commodities were so valuable in light of their potential applications that traders were willing to sail as far as South America by the late 1800s just to acquire them and sail them back to Europe. But that all changed in the second decade of the 1900s. That's when a German chemist by the name of Fritz Haber applied Le Chatelier's principle to a reaction of his own design. One that very quickly made these other forms of crop fertilizers practically obsolete. So let's take everything that we've learned about Le Chatelier's principle and see how it played into the development of one of the most important chemical reactions ever carried out by man. The Haber-Bosch process was developed a century ago by the famous German chemist Fritz Haber. Now, Karl Bosch was a chemical engineer, and he was tasked with scaling the process up for industrial applications, which is why the process so often bears his name as well. But it was Haber's genius that really was responsible for the initial development of this process. Haber developed a process for synthesizing ammonia. Ammonia is a very valuable commodity that finds use not just in agriculture, but in bomb making as well. And it was this last application that was no doubt foremost on his mind when he developed the process, as it was just as World War I was raging, and artillery was being consumed at a rapid rate by both the German army and its adversaries. Haber wanted to give his country a leg up by providing the necessary ammonia using nitrogen from the air. It was a bold endeavor, since only precious few life forms have been able to accomplish that task with 3 billion years worth of evolution and the power of biochemistry. But if he could pull it off, Germany would be able to acquire that critical ammonia that it needed using little more than air, while her enemies would have to continue mining and shipping other forms of nitrogen-containing materials from distant lands. Haber was in for a fight. But, as we'll see several times over this course, Fritz Haber was a man practically incapable of quitting anything he started. The reaction between Haber's proposed starting materials, hydrogen and nitrogen gases, is exothermic. This means it releases heat. It's also exceedingly slow at standard temperatures and pressures. So slow that it essentially doesn't happen. Now, Haber's solution to this was a twofold strategy to increase the reaction rate. Metal catalysts were used, and the temperature of the reaction was increased dramatically. Under these conditions, the reaction happened much more quickly. But you can probably see a problem coming now. Le Chatelier's principle predicts that increasing the temperature at which an exothermic reaction is run will push the equilibrium back towards products. In fact, this happens with the Haber-Bosch reaction, and so little product is obtained that it's not even worth running the reaction. But Haber wasn't going to give up. He knew that Le Chatelier's principle might have been working against him in the temperature department, but there are other ways to use Le Chatelier's principle to improve this process. So he ran his reaction not only at high temperatures, but at immense pressures. Pressures so high that his first productive reactor was crafted from the barrel of a warship cannon, the only object available at the time that could withstand the pressures and temperatures they were working with. Now, why so high? Well, because the reaction involves the conversion of 4 moles of gas into 2 moles of gas. And Haber knew that squeezing down as tightly as possible would encourage the mixture to react to undo that pressure he applied. This might counteract the effect of his high temperature requirement, right? Now, this strategy improved the process, but only slightly. Not much ammonia was formed at equilibrium. Even under the best of pressure conditions that he could muster, only about 10 to 15% of the gases inside of his reactor would convert to ammonia. Unrelenting, Haber applied Le Chatelier's principle again, creating a flow reactor, one in which the product from his reaction was passed into a cooler region, where the ammonia formed could be condensed into a liquid and collected, effectively removing it from the gaseous reaction mixture. The reaction mixture then flowed back into the high-temperature chamber to reestablish equilibrium, making even more ammonia. This final adjustment to the process was the key. Using Haber's design, German chemical giant BASF began to work to scale the process up to truly industrial proportions. Haber had succeeded in his primary goal of fixing nitrogen and extending World War I. So, in a somewhat fateful twist, the theories of a French chemist, Henri-Louis Le Chatelier, were used by the German chemist Haber to provide artillery that prolonged a war between their two nations. I'm not sure Le Chatelier would approve. But a secondary benefit to the development of this process was its effect on agriculture. As the First Great War wound down, nations around the world began adopting this new technology as a means of acquiring nitrogen, not just for explosives, but for fertilizers as well. In fact, it's so widely used that it's been estimated that about 1/2 of the nitrogen atoms in your body right now have passed through one of these reactors at some point in time. So today, we took a look at 3 ways that gas phase equilibria can be altered using Le Chatelier's principle. We can raise and lower the concentrations of reactants and products. We can raise and lower the temperature at which exo and endothermic reactions are run. And we can raise and lower the pressure at which many gas phase reactions take place, so long as there's a change in the number of moles of gas as the reaction progresses. And finally, we explored the Haber-Bosch process for synthesizing ammonia from nitrogen and hydrogen. And in doing so, we saw how Le Chatelier's principle guided Haber to success in his creation, probably extending a world war in the short term, but feeding billions over the past century. Chemical equilibria are all around us, and they don't just happen in the gas phase. From time to time as we move forward, we're going to encounter equilibria and continue to expand our understanding of how to model them as they appear. But we're ready now to move on to a new topic in chemistry. Next up, we're going to spend a series of lectures considering acids and bases.